Welcome to the Sleep Lab. Tonight we investigate a puzzle together. How can a super-Earth survive near a restless red dwarf star? Do rapid orbit, radiation, and tidal locking blur definitions scientists depend upon? Settle in and let your breathing slow. A distant telescope stared without emotion, measuring light instead of wonder. Tiny dimmings repeated, gentle and precise, like a signal tapping patiently on glass. No image ever arrived, only patterns quietly aligning. Numbers leaned towards certainty, ruling out shadows, background stars, coincidence. Through multiplicity, probability hardened into something undeniably real. The name sounds procedural, almost indifferent. Mission first, star number second, orbital order last. Yet beneath that cold structure, a massive world holds its silence. Kepler-186d lives beneath a small red dwarf sun. The star is cooler, spotted, slowly rotating through cycles of brightness. From the surface, it looms wide, salmon-colored, impossible to ignore. This world sits delicately on a boundary. Its radius stretches to 1.4 times Earth's, neither small nor swollen. Just beyond this size, planets inhale gas and forget solid ground entirely. Because of that balance, its nature stays unresolved. It could be stone layered with iron, dense and compact, or it may wear a thick gaseous veil, hiding any surface forever. If rocky, its mass presses heavily inward. 2 to 4 Earths worth of matter tighten its interior. Gravity there would deepen every step, turning movement into resistance. Some imagine water trapped beneath pressure. A global ocean, kilometers deep, capped by exotic ice phases below. Liquid dreams crushed into unfamiliar states, never touching air or light. Time behaves strangely on this planet. One complete year ends after just 13 Earth days. Orbit pulls it relentlessly close, far nearer than Mercury ever dares approach. Gravity grips this planet tightly to its star. Rotation slows, then stops, surrendering to tidal locking. One face burns under constant light, the other freezes in unbroken darkness without seasons or relief. The distance here is almost unimaginable. The orbit sits at 0.078 astronomical units. The star appears twice as wide, filling the sky with pressure and unblinking presence, constant weight. Eccentric motion adds subtle instability. The orbit stretches and tightens, never perfectly circular. Small variations change distance slightly, enough to alter heat, but never mercy during its brief 13-day year, always repeating. Seen from Earth, alignment is precise. The orbit tilts nearly edge-on, allowing repeated transits. Each crossing dims starlight predictably, confirming existence through geometry alone, measured patiently across years of observation cycles. Tidal locking erases seasons completely. Axial tilt fades, leaving climate fixed in extremes. Day never ends, night never lifts, and balance survives only in narrow twilight along the permanent terminator line zone. Heat dominates everything here. Equilibrium temperatures climb beyond 275 degrees Fahrenheit. Even before atmospheres interfere, the surface exists in a constant state of thermal stress and chemical instability. Some scientists compare it to Venus. Runaway greenhouse processes may trap heat relentlessly. Air thickens, surfaces soften, and any early oceans would vanish into vapor long before stability could ever form. Radiation never rests around this close red dwarf. X-rays and ultraviolet streams collide with the planet continuously. Each impact strips lighter gases away, thinning skies through slow, invisible erosion across millions of years. Magnetic protection is likely weak or absent. Without shielding, stellar wind reaches directly into the atmosphere. Hydrogen escapes first, then helium, leaving heavier molecules behind or nothing at all. Yet one region invites quiet curiosity. Between fire and ice lies the permanent twilight band. Along this terminator line, temperatures soften briefly, hinting at balance that never fully arrives. This system is crowded, compact, almost compressed by design. For inner planets race inside a space smaller than Mercury's orbit. They circle close enough to feel each other's gravity constantly, always nearby. Kepler-186d is the largest among its siblings. Despite size, it remains overshadowed by a quieter, farther companion. Attention drifts outward, while this world endures extremes unnoticed silently alone. Gravitational tugs ripple through the system like measured tension. Minute timing variations betray planets pulling on each other. These shifts confirm presence without sight, only motion and math working patiently over years. Age settles over the system, nearly 4 billion years deep. Comparable to our own neighborhood's long, chaotic history. Time shaped these worlds together, then locked their futures tightly through gravity, heat, proximity. Distance keeps this planet unreachable, 580 light-years away. Even light would need centuries to cross that separation. For now, it teaches through models, not visits or images alone patiently. Future instruments wait patiently beyond our current reach. Tonight together. During transits, starlight could filter through unseen atmospheres. Spectral fingerprints might reveal carbon dioxide, nitrogen, or emptiness itself, drifting across wavelengths silently. This planet matters because it sits on transition between rocky super-Earths and gaseous mini-Neptunes. Its radius quietly defines where solid worlds begin dissolving into envelopes of hydrogen and helium gas. Models test this world against heat and loss. Climate simulations strain under radiation and tidal locking. Each equation asks how long atmosphere can endure here before stellar winds peel it away entirely. This system teaches formation around common red dwarf stars. Low metallicity did not prevent Earth-sized bodies emerging. Heavy elements were scarce, yet planets assembled anyway inside a compact inner orbital architecture. Far away, this planet remains unseen and unreachable. yet it reshapes how scientists think about worlds. Kepler-186d becomes a benchmark written in light and heat, far beyond the comfort zones of habitability science. Beyond it drifts a quieter sibling, farther from stellar fury. That outer world receives gentler light and longer years. Together they outline extremes within one gravitational family, formed early and evolving slowly. Here, closeness writes destiny faster than chemistry ever could. Tidal forces knead interiors, reshaping mantles and iron cores. Heat, time, and gravity collaborate without negotiation until structures settle into permanence under stress. Crowded orbits amplify interactions, each pass slightly adjusting clocks. Transit timing variations expose these subtle gravitational conversations. Motion becomes testimony when light alone remains silent, across years of careful observation campaigns worldwide. Over billions of years, atmospheres thin or transform. Radiation selects survivors among molecules, favoring heavier remnants. What remains tells history through composition and pressure, locked beneath unyielding stellar influence continuously nearby today. This planet warns us about proximity and patience. Size alone cannot promise surfaces, oceans, or refuge. Context decides outcomes, written by stars and distance over immense spans of time and energy exchange. Researchers treat this planet as a laboratory for extremes. It tests climate theory under relentless radiation and tidal locking. Failures and survivals refine models predicting rocky worlds elsewhere around red dwarf stars. Its distance keeps certainty softened, 580 light-years away. Signals arrive old, carrying histories already finished at origin. We study fossils of light rather than living change in real time. Yet, even delayed information reshapes how planets are classified. This world sharpens the boundary between solid cores and gas. That edge defines expectations for countless surveys ahead across future missions and catalogs. Quietly, this planet reframes habitability by showing where hope fails. Earth size alone cannot overcome heat, radiation, and loss over geological timescales without exception. The environment writes outcomes with strict physical rules everywhere. As models improve, this world remains a quiet reference point for future telescopes and analyses. It anchors theories with real constraints from observation globally. Preparation builds toward the final answers still withheld. All along, the mystery waited inside measurement, not imagination. A super-Earth too close to its star must change. Physics tightens conditions, forcing outcomes that defy familiar planetary expectations entirely over time. Proximity accelerates every process here, from atmospheric escape to internal heating. 13-day years and tidal locking remove recovery. Heat accumulates, radiation persists, and balance never has time to stabilize naturally there. This is why definitions blur around this world. Size suggests rock, yet conditions invite gas. Kepler-186d exists where categories collapse, reshaped by stellar force instead of composition alone. The question was never about beauty. It was about survival near a red dwarf. Here, science reveals that orbit and distance outweigh size, turning Earth-like worlds into extreme outcomes over time. So the answer emerges slowly. This planet endures, but never settles. Kepler-186d survives as a heated, stripped, transitional world, defined by proximity, not potential, teaching limits clearly tonight. What began as a question becomes understanding. A planet can exist without thriving. Kepler-186d proves survival is not habitability, only physics patiently unfolding under relentless stellar influence across time. If this investigation slowed your breathing and sharpened your curiosity, remember science is deepest when shared. Like, subscribe, comment your thoughts, and share this journey. We continue uncovering quietly together.